In this last video of this week's lecture, we will look at some alternative architectures of recurrent neural networks that are typically used. So let's dive right in.
Alternate recurrent neural network models. Okay, so the LSTM networks that we learned in the last video are by far the most successful and most widely used recurrent neural network models. And they've really become a default model for application of RNNs. But there are also some interesting alternatives. First in the slide, let's look at gated recurrent units or GRUs. So these GRUs are quite similar to LSTMs. And this is because they're also built on top of the same idea of gated units, but they are a little bit simpler. And this is because they use an input gate and they only use a single gating unit that controls both the forgetting factor and the new contributions to the state update. So you can see the depiction of the GRU unit here. So R here is the input gate and Z here is the factor that is used in the recurrent mapping from the old hidden state to the new hidden state here. And it's also used to control the update of the cell state where the hidden state uses the new input candidate to give the candidate hidden state here. So gated recurrent units are also very popular and they work well for many applications. So it's not really clear whether LSTMs or GRUs are better for a given application. Sometimes one is better and sometimes the other. Whereas gated recurrent units have the benefit that they are slightly simpler and they have less amount of parameters. But overall, they both are competing models and they both do very well for any application that requires capturing long-term dependencies. Okay, so a very different recurrent neural network model is these echo state networks. So these were introduced in around 2021, 2022. And their idea is to have a large fixed part that we called as reservoir. And this is a recurrently connected part. And this has random weights. So we initialize the weights inside these recurrent connections randomly, and we don't really train them. So the idea here is to have rich connections and rich dynamics in this reservoir. And we use these outputs of these recurrent units as filters that you can see here. And these filters create a great variety of signals that we can then recombine to construct our output signal. And only the output layer actually in this case is trained, and we just use a linear regression. So you fix everything beyond the output layer. So only this part is the output here, and everything that comes before is fixed. So the input weights are fixed as well as the weights in the reservoir here are fixed. So the nice thing is that because you only train on these random filters or the random basis functions, so you do the regression based on these random filters here. So you don't have to do any backpropagation through time. So in fact, you can just treat this as basis functions as a linear regression that we have seen before, and you can just compute the output weights for the linear regression in a closed form. So that's very quick, and it actually has very good performance on many time series prediction tasks. And the introduction of echo state networks really led to the invention of this field of recurrent neural network research at the beginning of the 2000s, when LSTMs were not as widely used as today. And also the computational power to do large scale backpropagation through time wasn't really feasible at that time. So these are much simpler models. And even though they seem very simple, they can work quite well in practice for many problems. So one more property that I didn't mention up to now is that one needs to take care of the scale of the recurrent weight matrix to the spectral radius smaller than 1. So the spectral radius is the largest absolute eigenvalue of the connectivity matrix for the recurrent weights of the reservoir here. And this needs to be scaled so that this is basically smaller than 1. And this ensures stability and ensures that the dynamics of the networks don't amplify and saturate at some point. Okay, so the last model that I want to look at is the neural Turing machine. So this is a quite recent model, and there's also extensions of it, but the general idea remains the same. So the general idea is that we want to extend RNNs, that is down here. So this is a regular RNN. This can be an LSTM, for instance, and this acts as a controller network, and we extend it with these so-called memory cells. So this is an external piece of memory in this network, which it can use to learn to read and write to. And because it can read and write to this external memory, it can, of course, remember facts over arbitrarily long time scales. And this writing mechanism and reading mechanism are both implemented using attention mechanisms. So attention is something that you will learn in the next week. But for now, let's just say that these are implemented as neural network mechanisms, which are also trainable. So the nice thing about these architecture is that it can be used to train a model for tasks that require very long memory, for instance, such as natural language processing or question and answer task. And these models have been very successful in this domain. All right, so this brings us to the end of this video, and I have two questions for you. What are the main differences between an LSTM cell and a GRU cell? What are the key elements in these neural Turing machines that we saw? And what are the advantages of this over conventional LSTMs or RNN units? So that was the last topic for this week's lecture. Thank you, and I will see you in the following weeks.